So this lecture, this topic is sedimentary rocks, and the second part of the title here says weathering, erosion, and deposition. All sedimentary rocks are the products of other rocks. In other words, other rocks such as igneous rocks or another sedimentary rock or metamorphic rock, some other rock weathered. Weathering is a process where you break down the rock into smaller components, smaller pieces. Those smaller pieces then can be, after they're weathered, transported, which is erosion, and then redeposited someplace else into a brand new rock. So an example of that is our beaches in Huntington Beach. They're the result of granite that weathered. The quartz within that granite, because it has a very strong covalent bond, doesn't break down. It basically, chemically doesn't break down, it simply weathers into smaller pieces. And then it's transported by rivers, deposited out in the oceans, and the ocean currents transport that sand up and down the coast, and then the waves in the winter and the summertime deposit that sand onto the beaches, and that's where our sand comes from. So our sand is the product of weathering, erosion, the transportation. So the beach sands that we enjoy today at beaches like Huntington Beach, Seal Beach, Long Beach, are the result of granite that has been weathered out of the San Bernardino Mountains, the Santa Monica Mountains. All the granitic mountains to the east of us have weathered, and then that material has been transported by streams. So all sedimentary rocks are the products of other rocks. So granites, this is a typical granite. Granites consist of minerals like quartz. It consists of potassium feldspars, which have aluminum in them. As these minerals and these granitic rocks weather, they're going to form clays, they're going to form sands, they're going to form silts, and then the processes of erosion through water and wind are going to move these products elsewhere, redeposit them into brand new rocks we call sedimentary rocks. So the importance of sedimentary rocks. Well, oil and gas and petroleum comes from sedimentary rocks. Natural gases, salts for chlorine bleach, borates for making detergents, building materials, concrete, asphalt, all of these are products of sedimentary rocks. So of the three groups of rocks, sedimentary, igneous, and metamorphic, to me, sedimentary rocks are the most important, especially considering my field is more into the environmental ends of geology, understanding the reconstruction of past histories and how organisms evolved. And so sedimentary rocks tell a little bit more a complete story. They'll tell you who was living there through the fossils. They'll also tell things like climatic conditions, if it was wet, if it was dry, if it was cold, if it was warm. Where igneous rocks basically will tell you, you had a volcano, you had a plutonic rock, you had a magma body rich in iron or silica. But sedimentary rocks, they provide a far more complete description of the Earth's history. And it's because of sedimentary rocks that we have a really good understanding of the last 400 million years and the evolution of life. So sedimentary rocks are pretty straightforward as compared to igneous rocks. They were first studied by the English, so they have very common names, just conglomerates. This is the name that's used in business when multiple firms come together to form one corporation. Breccia is a similar rock to a conglomerate, it's just the fragments are angular. Sandstone, a rock consisting of sand. Siltstone, a rock consisting of silt. And shales are clay materials. So we basically have three classifications of sedimentary rocks. We have what we call the clastic or detrital. These are fragments of other rocks. So sandstone's a good example. That sand that's in that sandstone at one time was part of a granite. As that granite weathered, and then those components of quartz sand crystals within weathered down into small little round sand grain sizes, they were transported by water, wind, or a combination of the two into a new rock, into perhaps a sedimentary deposit like a sand dune, and then that sand dune can then be compressed into sandstone. Then there's the rocks that form in a chemical environment, and this is with water. So a good example is limestone, a very common sedimentary rock. Travertine, coquina, fossiliferous limestone, and chalk, all these pretty much share a commonality, is that they were all deposited because of shallow marine oceanic waters. So these are rocks that form at the bottom of very shallow seas. And then there's some other strange rocks, such as rock gypsum. This is also aided with water, rock salt. And then there's a biochemical classification of sedimentary rocks, and that comes under the form of coal. And we call this biochemical because there's a biological component in coal. There's organic carbon within coal, and that makes it a biochemical rock. So they're very economically important. Coal is a sedimentary rock because it has organic material. It doesn't fit the description of a mineral, so it is a rock. Petroleum, natural gas. They're also very important sources of iron, aluminum, manganese. The early iron mines that really provided economic wealth and stability to the United States were iron formations that were found in sedimentary rocks up in Michigan. Offshore, there are sedimentary rocks in deep water basins that have been enriched with hydrocarbons and organic material. Accumulation of those hydrocarbons over time compresses and it forms coal. So this is why we have offshore rigs all along the Pacific Coast Highway around Huntington Beach. Water, though, is the most important agent when it comes to sedimentary rocks. It is the most erosive force in nature. So a lot of people think wind is really erosive, and wind is to a point. It will move particles, but nothing like water. In fact, of all the natural disasters, more people are killed each year in flood-related incidents than any other natural disaster. So water is the most important force. It's responsible for breaking down rocks. It aids in the chemical reactions of the breakdown of minerals. It aids in the transportation of those rocks. It aids in the deposition of it. So sedimentary rocks are heavily influenced by water. So this is a good example. This is a formation in the Arizona desert called the Monocope Formation. And this was a formation that was basically deposited for very shallow streams, very water-rich environment. And today, this formation is being broken down and weathered because of water. So water is very erosive, but it also is responsible for formation of a lot of the sedimentary rocks that we see. And the place that holds true to this is probably one of the best examples is the Grand Canyon. So the rocks that we see today in the Grand Canyon were formed in a water-rich environment in a very shallow sea that flooded the North American continent. So today, this is a portion of the Grand Canyon where all of these sedimentary rocks here were deposited in oceans. Today, they're being exposed because this area has been uplifted due to tectonics. And as the area uplifted, the Colorado River slowly cut down through, exposing these stratigraphic layers. And so the Grand Canyon gives us a really good chronological history of the Earth from, billions of years ago all the way up to the Kaibab Formation to about 300 million years ago. So we have a really good early ocean life chronological history exposed in rocks of the Grand Canyon. So the Grand Canyon, if we're to go back in time, 400 million years ago, this is what Arizona would have looked like. It was a very shallow continent, didn't have mountain ranges, very low landscape, and it was flooded by the oceans 4 different times. So if you were in Arizona, if you were in northern Arizona where the Grand Canyon is today, 400 million years ago, you'd have been in an environment just like this. You'd have been surfing. And we see a sequence of rocks that we see today at modern coastlines. We see that same sequence in rocks that are hundreds of millions of years old in the Grand Canyon. So if you look at sand on a beach, take a handful of sand, look at it with a magnifying glass or a microscope, you'll see within that sand, the major component is going to be quartz. Very fine grains of quartz sand that weathered out of igneous granitic rocks. In our case, the beaches of Huntington Beach originated from the weathering of granite in the Santa Ana Mountains and even in the San Gabriel Mountains. The Santa Ana River has transported that sand from San Bernardino County through Riverside County into Orange County and eventually out into the ocean by way of the Santa Ana River. So the Grand Canyon is a good example of rocks that were formed in a very water-rich environment. These are very shallow epicontinental seas. These are seas that flooded the North American continent. Today, what is northern Arizona is mountains. So how did this at one time, why was it an ocean at one time, and why is it today a canyon that sits 6,000 feet above sea level? Well, 400 million years ago, Arizona was flat. It was much like Florida is today. No mountains, very flat landscape. And as sea level rose, it flooded over the North American continent, and it deposited a sequence of rocks, and we can see that. We can see beach sands, we can see tidal flats, and we can see marine limestones, all in the Grand Canyon. The same thing we see today, we see in the Grand Canyon, only these formations are hundreds of millions of years old. One nice thing about sedimentary rocks is they are the best rocks for studying fossils. In fact, igneous rocks do not contain fossils at all. Some metamorphic rocks do contain fossils, but here's a primary example of where these fish died rather suddenly. There was a catastrophic volcanic explosion. That volcano resulted in a very high intensity of ash. That ash then went into this lake, settled, and the fish died really quickly, and they were quickly buried and quickly preserved as fossils. Interesting thing about this is that this is a fish that is a catfish that today we find off the coast of Florida, southern Florida. But yet these rocks are in Montana. So this tells us that at one time, climatically, what is today a cold climate, Montana and Wyoming, was very warm, almost subtropical like Florida. And this is one of the neat things about fossils is they'll tell us. And so this is a fish that was buried in the middle of eating lunch. So here the big fish was eating the smaller fish, the volcano exploded, that lake was instantaneously engulfed in ash. This fish in the middle of eating lunch was buried and preserved as a fossil. Throughout the Grand Canyon you'll see a lot of trace fossils. Sometimes you won't see the fossil itself, but this is an organism that was moving through the sediment, stirring up sediment, looking for something to eat, a bottom feeder. The quarter is there for scale. And so today we see modern sand dunes. So here's a modern sand dune with ripple marks in it. And often these ripple marks are preserved in sandstone rock. We can actually see the ripple marks as they were preserved in the sand dune, which is now a rock we call sandstone. So by looking at modern landscapes and then looking at ancient rocks, we can correlate on what's going on today. And so geologists kind of use a saying that current conditions are a key to the past. So we see rivers cutting into canyons today. So when we find an ancient canyon, we assume that that canyon was cut by a river. When we see ripple marks in sand, we assume that those ripple marks are either created by wind or by water. And it depends on the frequency of the ripple marks, whether it was deposited or formed by water or wind. So sandstone. You can take a sand dune, you can compress it into a rock, and we call it sandstone. And as it turns out, sandstone rocks, they have the general characteristics, the same patterns, the same shapes as modern sand dunes. So when we look at rocks that are 100 million years old, we know that 100 million years ago that these rocks were once a sand dune, and that sand dune was compressed over time and formed into a sandstone rock. Now this sandstone rock can actually weather out back in the sand again and form another rock. So nature constantly recycles, and this is what sedimentary rocks are. So this is a close-up picture of a sandstone. Probably not coming up very good in the media that we're using here, going from the PowerPoint to the projector to the screen, back into a camera, and back onto YouTube. But this is a very sandy texture rock we call sandstone. So physical processes. So these are two things I want you to know. Weathering and erosion. People confuse these terms. So weathering is a physical breakdown, the disintegration into smaller pieces of rock. So you can take any rock, an igneous rock, a sedimentary rock, a metamorphic rock. You can break it down into smaller pieces, that's weathering. Now there's different types of weathering. There's physical weathering. So glaciers is a good example of physical weathering. So as glaciers move across a landscape, they act like sandpaper and they grind down the rock. That's a good example of physical weathering. Ice can get into cracks of rocks or water, and then at night that water can turn to ice, expand, push those grains apart. Tree roots can do the same thing, so those are good examples of physical weathering. And then there's chemical weathering. Chemical weathering, basic, it's acid. So water combines with other compounds or elements to produce acids. And it's the acids that are probably the most important weathering process of sedimentary rocks. So weathering, there's two types. There's physical weathering and there's chemical. And then erosion. After the rocks are weathered, they're broken down to smaller pieces, then those rocks can be transported. And that's what erosion is. Erosion is the physical removal of weathered material by either water, wind, ice, or a combination of those things. So erosion and weathering are completely different. You have to have weathering before you can have erosion. You can't erode an entire mountain range. You have to take those components in that mountain range, those rocks, and break them down to smaller pieces. And then mass wasting basically is when we have something that dramatically occurs, like massive soil erosion or a landslide. And this basically is due to the influence of gravity. So sedimentary rocks, all sedimentary rocks are particles, parts of other rocks that have been physically, chemically, or mechanically broken down. These particles are then collected and cemented and then compressed into a new sedimentary rock. So let's look at the types of weathering. So mechanical weathering, breakdown of rock. So this is a physical process where the rocks are being subject to some type of force. Tree roots are getting in between the rocks and pushing them apart. Ice is acting like sandpaper. Frost wedging. Thermal expansion. So as it turns out, rocks become heated and they cool. So as they heat and cool, they expand and contract. That creates cracks. Water getting in between those cracks and cause more erosion, breakdown of that rock, weathering. And biological activity certainly is roots from plants. So here's a good example of a mechanical weathering. Daytime, water will seep into cracks of rocks. Nighttime, the temperature drops. That water then turns to ice. As water converts to ice, it expands. And that expansion then causes the grains to be pushed apart. So that is a good example of physical weathering, ice wedging. And then chemical weathering is probably the most important. This is basically where we now chemically break the rocks down. We attack the very soft elements, the iron-rich elements, so water can get in and find iron within a mineral. And actually oxidize that iron, breaking that mineral down. So you break down the minerals, you start to break down the whole rock. So water gets in and gets into the really fine matrix of the rock, gets into the minerals, and looks at the iron. And so iron is very subject to oxidation by water, turns to rust basically, and this basically helps break down the rock. So the most important agent is water. So basically what water does is it transports the ions, it picks up other chemicals. So water can pick up calcite, which is very common mineral. So water plus CaCO3 forms H2CO3, which is known as carbonic acid. And so then this acid goes to work and really breaks down some of these minerals. So as it turns out, a lot of the minerals in granites break down because of the acids. But one is very resistant to the weathering by acids, and that is quartz. And quartz, SiO2, has a very strong covalent bond, so it resists chemical weathering. It resists that whole process. So what quartz does is as it's transported, it wears down, but it still remains its integrity. It's still quartz. So by the time you take a large quartz crystal, transport it, and it tumbles through the stream bed and becomes smaller and smaller and smaller, and it winds up as beach sand, it's still quartz. It's still SiO2, it hasn't broken down. The other minerals and granites break down in the clays. And it's because of weak ionic bonds that water can get in there and break these rocks down. So this is better known as a dissolution and oxidation. All of these are basically aided by water and then hydrolysis. So dissolution, small amounts of acid are picked up with water. So water picks up calcite, it can pick up sulfur to form sulfuric acid. It can pick up chlorates to form hydrochloric acid. There's a bunch of different acids, and all the acids act on the minerals, breaking up the internal matrix of the chemistry of those minerals, oxidation of iron grains. So anything with iron, it's going to oxidize. So any mineral with iron in it, it's going to break down. And a lot of the minerals in granitic rocks contain iron, so they break down fairly easily. And then hydrolysis is basically when hydrogen either replaces another ion through water. So this is where, again, a chemical reaction where the integrity of the mineral is compromised. Once the mineral integrity is compromised, the minerals fall apart, the rock falls apart. So this is why it's important that we have to have weathering first, and then we can have erosion. So basically what it does is decomposition of unstable minerals. So the unstable minerals, it turns out, are the iron-rich minerals. They fall apart. Plagioclases fall apart. They contain minerals like potassium and aluminum. The aluminum will actually go to form clays. And quartz is very stable. It just simply stays together though. It doesn't break down like the plagioclases and the micas. The micas disintegrate. And so what happens to quartz is it basically physically changes into the rounding. So this is a chart showing minerals that are in a granite quartz. Quartz breaks down in the quartz grains, plain and simple. The feldspars, amphiboles, all these other minerals, they break down in the clay. They break down in the rust. And this is why granitic rocks can fall apart. And the resilient mineral is going to be quartz. It's going to be transported by wind and water, and the combination of those two is going to form sand dunes in the desert. It's going to form beach sands on our beaches. So the rates of weathering are basically affected by the greater surface area, the more exposure of a rock, the faster it's going to weather. Other things, such as the mineral makeup of the rock, and also the climate conditions. So rocks that are exposed to very tropical environments where you have lots of moisture and ample heat, those rocks weather much quicker. There are rocks in the Mojave Desert that are 17 million years old and they haven't weathered at all, volcanic rocks. But yet those same type of rocks in places that are tropical, like Hawaii, that are 400,000 years old, have broken down into soil already. And that's basically the influence of climate. So there's a lot of things that affect the weathering of a rock, the makeup, the minerals, and the climate. So as it turns out, this is Bond's reaction series. We use this in identifying igneous rocks. And so as it turns out, quartz, this is the mineral that's most stable. The rest of these minerals are unstable. Olivine, lots of iron, breaks apart, oxidizes, turns to rust. Same with pyroxene, lots of iron in pyroxene, lots of iron in amphibole. There's iron in biotite. The sodium, potassium feldspars. These feldspars have many different elements in them. Many different elements make up those minerals, and they're very easily, bonds are broken, resulting in a disintegration of those minerals. So quartz is the most resilient one, and it's because quartz is resilient to weathering because of that strong covalent bond. This is why reason we have sand dunes. This is the reason we have sand in our world. Why we have sandy beaches. So obviously, if you increase the area by cracking a rock, that's larger areas that can be attacked. So this gets into the mechanical weathering. So thermal expansion and contraction creates cracks. Then solutions get between these little cracks, create more cracks, and create a greater surface area of weathering. So climate is a very important influence. Temperature and moisture. So in tropical areas where you have higher temperatures and lots more moisture, rocks are going to weather much quicker. So in the Mojave Desert, there are these volcanic rocks that are 17 million years old. And we find that almost identical sedimentary, or not sedimentary rocks, igneous rocks, basalt flows that are 17 million years old. We find these rocks in the Mojave Desert that are 17 million years old. Same rocks in Hawaii that have already broken down into dirt, in the soil. And that's because of climate. So here's a good example of mechanical weathering, where these rocks have been subject to thermal expansion and contraction. This solid mass of granite cracks. That allows water to get in there. It can ice wedge at night and push the rock apart further. Because of these cracks, water and solution can get in between these cracks, carry with it acids, and this is the process in which rocks break down. So the Mojave Desert in Hawaii, those are volcanic rocks in the Mojave Desert of California that are 17 million years old. These are basically basalt flows. Same formation in Hawaii. Same iron-rich, basaltic rock, aphanitic texture, yet these rocks are 400,000 years old and they've already weathered and been transported and eroded, and they form soil. And why? Yeah, the blank screen, that's why. Why? Because of temperature and wet water, which my slide went away. All right, so eventually what's going to happen? All these rocks are going to weather. Then they're going to be subject to erosion. So they're going to be moved someplace else and then redeposited into sedimentary material, into sediments. So this is where soil comes from. So soil basically is a combination of mineral, organic material, excuse me, water and air. So there's basically 4 components that make up a good soil. Mineral, which comes from the rocks, organic material, a very small component, water, and air. So those are the 4 components that make up a good soil. So the organic material varies, and it's largely dependent on climate. So for example, in deserts, there's not a lot of organic material in deserts. So desert soils are deficient in organic material. They're very rich though in mineral material, and they're very poor in water. So you have to have those 4 components in the right amounts, and this pie chart will kind of show that. So definitely want you to know this. I'll ask this as a question on the quiz. So a good soil is going to consist of about 25% air, 25% water, 45% mineral. So this comes from rock basically. This is weathered rock, the mineral component. And then it's the organic component. So what's the organic? This is dead plants, dead animals, all the things that come off of trees that lay at the bottom of the forest to form things called mulch. That's the organic material. So this is the composition of a really good soil. And then what really determines a good soil is the parent material. So as it turns out, some of the best soils in the world are found right next to volcanoes. So volcanic rock is rich in iron. And so iron is a really important component in a soil. You need a soil that's rich in iron and magnesium. This is why people grow bananas, which are a good source of potassium, a good source of iron. Pineapples, good source of iron and magnesium too. Those particular fruits are basically raised on farms that are right near volcanoes. This is where volcanic rock has broken down into good soils. So the parent material of rock is really important. So volcanic rocks make very good soils. Carbonate rocks, calcium carbonate. These are limestones that you see like in the Grand Canyon. They make very poor soil. They don't have any good, useful minerals in them. They don't have any iron. They don't have any magnesium. They don't have any potassium. So as a result, they form very poor soils. And the amount of time. So soil is a non-renewable resource. And we're depleting our soils throughout the world today because of overgrazing, farming practices that are archaic. And so we're losing soils at a time when we need more agricultural lands due to increases in populations. So we're definitely losing our soils, and soil is a non-renewable resource. So climate is going to be a big contributing factor to the development of a soil. And then organic material and topography. So as it turns out, you don't find good soils in mountains because it's too steep. when it rains, that loose soil can be washed away. So where's the best soils? In valleys, basins, like where we live. So Orange County, named Orange County because of orange groves. At one time, that's what dominated Orange County. Today, the orange groves are gone. We replace them with freeways, concrete, houses, condominiums, shopping centers, and all sorts of wonderful things, schools. And so topographically, areas that are very low, flat, like basins like Orange County, the LA Basin, are very good for the accumulation of soil. So here's basically a diagram that shows that. This is what Orange County used to look like. The Santa Ana River used to be a meandering stream, meandered back and forth. Today we've channelized it and it goes straight. We've replaced the farm fields, Irvine Ranch, all the historical farms are now gone and replaced with streets, concrete, buildings and houses. And so where we live, very good soil. Up in the Santa Ana Mountains, poor soil. And the reason for that is that because of the topography, because of the steepness, those soils erode away. They wash away. So a good soil profile, there's different layers of her, and I'm not going to get too far into this. There's actually a sub-discipline in geology where people study soils. You can take an entire course for an entire semester just on soil classification. I took one of those courses once, and once was enough. So there's different horizons, so I'm just going to go to this picture. I think shows very good. So here's an ideal soil. Not the case for Orange County. So for a really good, idealized soil, where would you find something like this? Certainly in the Midwest, in Ohio, places like that. Maybe in the southeastern United States, in places like Georgia, Alabama. So you have the parent materials, the rock, that's at the bottom. This is going to weather out. And then this is going to be altered rock, a little bit of clay mixed in. And then the B horizon is going to accumulate to clay. And this is where basically water and organics all kind of come together. And then this is where you get a lot more clay and leaching going on. And then you get the mineral matter is mixed with the organic material. So the O horizon is basically the organic material. The A horizon is mineral matter mix. So what do we have in Orange County? We have a lot of this. We have too much clay in our soil. We don't have enough sand in our soil. Our soil is too clayey. It kind of clumps together. What's bad about clays is they tend to restrict the transport of water, where sand will allow water to flow through it and it'll act as a reservoir. So we need to really have a little more sand in our soil. So we basically have about 3 horizons in Orange County soil. We have a lot of clay with a lot of mixed up weathered rock. We have some organic material. And then we have a little zone with, we really need more sand in our soils. So this is actually a soil that a profile of a soil I took out in an agricultural area. This soil kind of has 3 profiles. This is typically what you see in Orange County. You find the broken up rock down here, a clay layer, and organic material. And that's basically what our soil horizon in Orange County consists of, about 3 layers. So soils are classified. A lot of that classification is due to climate, where those soils occur climatically. So here's some of the classifications. Oxy soils, soils that are oxidized. So there's different soils, and a lot of these classifications of soils are based on climates. So like this one here, arid soils. Young soils, which are parent materials, volcanic ash and cinder deposit, recent volcanic, well that's end soils. Arid soils in dry places, so soils that are developed in dry places, insufficient water to remove soluble minerals. We have the accumulation of calcium carbonate, which is not good, gypsum, or salt, very poor soil. This is what you typically see in deserts. And it's amazing that people have tried to grow crops in these areas and have failed tremendously failure. Soil erosion is a big part right now, especially since we're deforesting the Amazon basin. The Amazon basin is basically, the soils are washing away. And the Amazon River, which used to flow a green color, is now flowing a brown color. So as we cut down the trees, when it rains, those trees and that vegetation is no longer there. And used to act as a barrier to soil erosion, so it was stability. So we've taken out the stability, we made these areas very unstable, and then when weathering patterns occur, such as rainstorms, those rainstorms then wash those soils away into the Amazon basin. So our deforestation is having huge consequences on the overall ecological environment of the Amazon basin. So natural rates of soil erosion depend on soil characteristics, what's in it, the climate, the slope, and the type of vegetation. And this is probably where we've impacted soils the greatest. The human invention is that we take an area and we remove all of the native vegetation, and then we introduce the crops that we want. So there are some crops, there are some natural vegetations that hold in soil. They make it more stable. And when we remove those, they destabilize that soil. And a lot of plants that we plant actually take a lot of the nutrients out of the soils very quickly. And this basically results in the breakdown of these soils. So soil erosion occurs when the amount of replacement of soil is outpaced by the removal of soil. And agriculture certainly impacts this. So we have a big problem with that in the lower Colorado River right now. So the Colorado River, which originates in Colorado, in the Rocky Mountains, flows through the state of Colorado into Utah and then Arizona. Then it flows along the Arizona-California border. And all along that corridor there, we're dumping a lot of sediments, pesticides, fertilizers into that river system. And by the time that river flows into Mexico, there is so much suspended solids in there that the water is really a low quality. So we impact soils through water pollution, through the introduction of non-native species, through the removal of the native species. So we kind of destabilize soil on large scales. So let's get at sedimentary rocks. Sedimentary rocks form as soil or eroded material first. So an igneous rock can break down. This quartz grains, the sand's going to go off and form a nice little sand dune someplace. That sand dune can lie around the surface for millions of years. It can become then buried, compacted, and cemented into a new rock called sandstone. So then, after their soils for a while or dirt, they then solidify into sedimentary rocks. And there's three classifications of sedimentary rocks. There's clastic or detrital. So the Greeks tried to get into sedimentary rocks too. Detrital is a Greek word meaning dirt. Clastic is an English word, simply means fragments of other material. And that's what most sedimentary rocks are. They're fragments of other rocks. So a sandstone is fragments of sand quartz grains that came from a granite. Chemical rocks, they were precipitated in a solution. In other words, at the bottom of an ocean, in a lake. And then there's biochemical. It has an organic component to it, and the true only biochemical rock is coal. So coal is a biochemical rock, gets organic material. So here's a good example of classic sedimentary rocks. These are sandstones. This is part of the Aztec / Navajo sandstone. This is a formation that covers eastern California, southern Nevada, Arizona, Utah, Colorado. It's a very vast formation. At one time, these sandstone rocks were a sand dune. So if you were to go back to the Mesozoic, 200 million years ago, today what is Utah, northern Arizona, western Colorado, southern Nevada, eastern California was a massive desert like the Sahara Desert is today. Sand dunes everywhere. Those sand dunes were then later compacted into a rock we call sandstone. Now today this sandstone is weathering back out, back in the sand again. It can be carried by the wind, form another sand dune, and this process can repeat itself. For some reason this thing's going blank on me. A good example of a chemical rock. So the sandstone is classic, it's fragments of other rocks. Chemical rocks are rocks that are formed in water. So a good example is the Grand Canyon. The Grand Canyon formed as a result of oceans flooding the North American continent 4 different times. And we know this because the rocks tell a story. So I took this picture in the Grand Canyon. I was on a rafting trip. And so I'm in a raft. I took this picture. And where is one of the other rafts, part of our group? And so this is a raft that holds about 14 people. And so here's the raft, and here's the river, and look at the size of the Grand Canyon. So this is a massive canyon. And these formations are thick, such as the red wall limestone. So this is a formation that was formed in a water-rich oceanic environment. So this is when shallow seas flooded what is today northern Arizona. So all of California, Nevada, Utah was flooded by these epicontinental seas that flooded the North American continent. And so today, if we look at a modern beach, we see a sandy beach, we see the tidal flat where the waves break, and we see the ocean. So there are 3 different rocks that are deposited in this environment here. This is going to be your sandstone. This is going to be your shale, which is clay minerals. And then out here is going to be the limestone rock. We see this same sequence today called an environmental facies. So this is the beach facies. Out here where the waves are breaking, that's the tidal flat facies. And out in the bluer water here, this is the limestone facies. These environments are preserved in the rock we call the Grand Canyon. Wegener, in 1915, talked about coal deposits that were out of place. Wegener recognized that coal is an organic rock. It's rich in organic material, dead fragments of plants and animals. We see those environments today. This is actually a picture I took down in Arkansas. This is the southern portion of Arkansas near the Louisiana and Mississippi borders. And this is a perfect example where this is very stagnant water. All the leaves and matter that falls off these trees is going to wind up in this water. If you walk into this water, the mud is dark and it smells like sulfur. So this is the type of environments where coal is formed. And Wegener recognized that. So this is a good example of a biochemical rock. So come back here, the same spot, a couple 100 million years from now, it's going to be a coal deposit. So what is a sedimentary rock? So sedimentary rocks are products, mechanical and chemical weathering of other rocks. They contain evidence of past environments such as deserts, oceans, rivers. The southern United States, Nevada, California, we have a really good representation of sedimentary rocks. In fact, people come from all over the United States, all over the world, to look at the rocks in the western United States because they're so well exposed and there's such a large representation of sedimentary rocks in different environments. I mean, we find a whole sequence of oceanic flooding over the continents. We find salt deposits and evaporite deposits. We find gypsum. There's just such a vast record of sedimentary rocks in the southwestern United States. And often when I lead field trips, we run into people from Germany who are out here just to study the rocks. We run into students from Eastern universities such as MIT who come out in the desert here to study our rocks. What rocks tell us is they tell us a story. So back during the Mesozoic times, early part of the Mesozoic, this is what the western United States looked like. So here's California. Didn't really exist at that time at all. So geologically, California is a fairly young state. Most of our geology came from someplace else. And so throughout Nevada, Utah, there was these very inlet seas that came in. Very tropical at that time. We see that today in the rocks. So if you look at the rocks that make up the Grand Canyon in the southwestern United States, in the Grand Canyon, at the very bottom of the Grand Canyon is a formation called the Tapete Sandstone. That at one time, during a time period called the Cambrian, that was the beach. Above the Tapete Sandstone, you hike up the Grand Canyon a little bit further, you run into a shale formation called the Bright Angel Shale. That Bright Angel Shale represents a tidal flat. So this is where the surfers would have been. And then you go up a little higher in the Grand Canyon, you hike up into a formation called the Moab Limestone. This represented the ocean. So we see the same sequence we see today in rocks in the Grand Canyon. And so this is why sedimentary rocks are really important. They tell a complete chronological history of the Earth's evolution. And this is what's neat about the Grand Canyon. It's like a book. So once you can understand rocks, and you can read the story that the rocks will tell you, you have a good understanding of how the Earth formed. So we know that these rocks that make up the Grand Canyon are hundreds of million years old. Recently they've been uplifted due to tectonics. And then the Colorado River has cut down through these over the past 3 million years, exposing these rocks. So we have a really great record of sedimentary rocks in the western United States. And we find this sequence in other places. So this is actually just east of Las Vegas, Nevada. This is a mountain range called Frenchman's Mountain. And here these sedimentary rocks, the same sequence. At the bottom, you find the Tapete Sandstone, which represents the beach. Then you find the Moab, the Bright Angel Shale, which represents the tidal flat. And further up, you find the Moab Limestone, that represents the deep ocean. So we see this sequence repeated throughout the world. And this is why sedimentary rocks are really important. Titus Canyon, so this is actually in Death Valley. These are limestone rocks. And what these limestone rocks are is they tell us a little bit different story. There are no beach deposits here. There's no tidal flats. This is just all limestone. So this tells us that this part of California, during that same time period, was a deeper sea, a deeper ocean. You don't find fossils because fish and aquatic animals don't live in deep waters. They live in waters near the continents. So limestone rocks in Titus Canyon and Death Valley tells us that this area of California, when Arizona was a shallow sea, California was a deep sea. And we see the evidence of fossils in the Grand Canyon, but we don't see that evidence of fossils in deep water limestones. So again, by looking at those rocks at the bottom of the Grand Canyon, they tell us that at one time a very shallow sea flooded a good portion of the western North American continent. So all of Utah, most of Arizona, all of Nevada. There is no California yet. And that these oceans transgressed over the North American continent. They then regressed. They came back again, regressed, transgressed again. They did this 4 different times. And we see the same sequence repeated in the Grand Canyon, where you have sandstones that represents the sandy beach, shells that represent the tidal flats, and limestones that represent the oceans. Then you see that sequence repeated. So we know that the oceans flooded the North American continent during a geological period called the Paleozoic, from 400 million years ago, all the way up into the Mesozoic. And we can see this primarily because of the rocks. So the early development of the North American continent was an ocean. This is where the rocks of the Grand Canyon were formed. And then once those seas left the North American continent, there was a little bit of uplift. So the topography raised them up a little bit. And then, because of plate tectonics, North America kind of drifted from the tropics a little bit north into about 30 degrees latitude. And that allowed for the formation of a huge desert. And so during the mid part of the Mesozoic, what is today the southwest United States was this huge desert, a sand dune desert, much like the Sahara Desert today. So this is what the landscape looked like throughout California, throughout Nevada, Utah, and Arizona especially. And when I say California, I'm talking about extreme eastern California. Western California quite isn't there yet. It comes much later. So these sand dunes were then buried, compacted, lithified into a rock we call sandstone. And today, this sandstone is eroding. And the reason you have these great big arches here, this is actually Arches National Monument in Utah. The reason you have these big arches here is this is because of chemical weathering. So today, this rock was a sand dune. At one time, it was actually a granite. The granite weathered. The quartz sands were transported to form great big sand dunes. Those sand dunes were then compacted into sandstone. Now the sandstone's being weathered again. And this is a good example of chemical weathering. So these little arches that you see here, these big arches actually, they start out as little holes. And this is because water moves through the rock, brings with it calcite. The minerals then precipitate out. And as the calcite crystals grow, they push the sand grains aside. They create a cavity. And that cavity over time gets larger. So it's mostly due to chemical weathering. And then the winds come along and help polish it. A lot of people think this is all wind erosion. It's not. It's mostly chemical weathering. And so this is where nature is constantly recycling. So a good example of erosion, wind can pick up sand. And this is a common phenomenon that we see down in Arizona. I actually saw one of these this summer, where eastern Phoenix was inundated by monsoons that came across. So you have a frontal boundary come across, moist, against 118 degree temperature that's dry. You get this huge boundary between these two systems. The winds pick up tremendous speeds, 60 miles an hour, and they pick up all the sand. So this is a good example of erosion. I've been stuck in some of these. I was actually surfing down in Baja a couple years ago, and there's a windstorm that lasted for 3 days. You can see where you're going anywhere. So it's amazing just how powerful the forces of nature are, such as water and wind. Even wind is a very prominent force when it comes to moving material, transporting it. So because of this, when those granites were weathered away, they deposited great big sand dunes. All of Utah was a huge sand dune. So was southern Nevada, and eastern parts of California, and parts of Arizona. And then these sand dunes were later compacted into rock we call sandstone. Now the reason this sandstone is red in color is because there's a little iron in there. And this iron is then oxidized, and it forms a sandstone that we call hematitic sandstone. And this sandstone is found throughout the southwestern United States. So here's a good example of weathering. So this sandstone is now weathering back into sand again. That sand can then be compacted into a new rock we call sandstone, sand dune, and then back into a sandstone again. So if you look at a modern sand dune, and I had a professor actually do this, he cuts into this sand dune after a rainstorm, takes a shovel, cuts into it, excavates into the sand dune. There's a modern sand dune out in the desert. This next shot is going to be a close-up of right here. And you can see that there's a feature called crossbedding. So what crossbedding is that in the deserts in the southwestern United States, typically the wind in the wintertime blows out of the northeast. During the summertime, the winds typically blow out of the southwest. So you have two different directions of wind depositing sand in two different directions. So we see this in modern sand dunes. And when we look at old sandstone deposits that were once sand dunes that are now sandstone rocks, we see the same feature. So we see this throughout Utah and Colorado, where you see these crossbedding patterns in the sand dune. So this tells us that this sandstone deposit here at one time was a sand dune. And the reason for that is simply the characteristics that we see today in a modern sand dune are the same that we see in this 200 million year old rock called sandstone. So that's why geologists and scientists feel that this rock formation at one time was a sand dune. So we look at the characteristics, we look what's in that rock, we look at bedding patterns and directions of deposition, and we use a lot of different tools to make these determinations. So how do you turn sediment into rock anyway? There's a lot of changes that occur. So once the sediments are out to like a sand dune, it can be buried. You can go through a process called diagenesis. Diagenesis is basically chemical, physical, and biological changes that take place. A lot of people are kind of really focused on biological right now. They see a lot of organisms secrete materials that are essential for cementing rocks together. And so this occurs in the upper few kilometers of the Earth's crust. So basically, sand can be compressed into a rock called sandstone. That rock can then weather back out in the sand again. That sand might be deposited in the bottom of an ocean. And so there's all different environments in which we look at for the deposition and the formation of sedimentary rocks. So when we look at sedimentary rocks, we look at really, much like igneous rocks, we look at the textures. And there's basically two major textures: visible grains or no visible grains. So rocks that have visible grains, particles, fragments, pieces of other rocks that have been cemented together. If they don't have particles and pieces of other rocks, then we call those non-clastic. And they're either be a chemical or biochemical. That means they were formed in the bottom of an ocean. So a good example, limestone rock does not have fragments of other rock in it. Sandstones do. So do shales, and so do rocks like conglomerates and breccias. So let's look at the difference between this clastic and non-clastic rocks. So clastic or detrital means fragments of other rocks. Chemical or biological rocks means that they were formed in a water-rich environment. So we already talked about diagenesis. This includes the recrystallization, the development of more stable minerals from less ones. Lithification, this is where sediments are transformed into solid rock by compaction. So compaction occurs because of burial. Natural cements, so calcites and natural cement, silica, iron oxide, all these are natural cements that take those sand grains and cement them into rock. But they usually do that because they're compacted, because they're buried. And then water can move through them with the compaction, turn them into rock. Now tectonics can uplift those rocks back up, bring them up to more higher altitudes, where they're then subject to weathering processes and then erosion. So here are our classifications for sedimentary rocks. Detrital or classic rocks, so classic or detrital, are fragments of other rocks. So if you have gravel size, we call it conglomerate. And so what's the difference between conglomerate and breccia? Is that conglomerate is well-rounded grains, and breccia is angular grains. And then sand-sized material is where we form sandstones. And then silts and clays are going to form siltstones and shales. And then all the other rocks were formed in a water-rich environment. So limestone was formed in an ocean. Travertine is actually formed in caverns. Coquina is basically right at the shore where you find a bunch of shale fragments that have been broken up and cemented back together into a rock called coquina. Phosphoriferous limestone is limestone that contains fossils in it. Chalk, you loved it as a kid. Basically chalk is microorganisms, lots of diatoms. Microorganisms that lived in a very rich environment like a lagoon, forms chalk. In Australia they call those billabongs. And then there's the sedimentary versions of quartz called chert. This is quartz that's formed at depth, buried deep. Petrified wood's a good example of that. Gypsum is formed in very shallow lake environments. Salt, rock, which has halite in it, or rock salt, as it's often referred to, is formed in a very desert environment where you have periods of flooding, and then it dries up, then flood comes along again, dries up again, and this is how salt crystals are growing. And then bituminous coal. So we're going to stop here. I'm going to break this into 2 lectures, and we'll classify sedimentary rocks and look at sedimentary rocks in detail in the second lecture. So I'm going to put this on hold for now, and we'll do the second part